We're going to do the first 15 minutes of notes for section 3.4. Section 3.4 discusses concavity. So we've already discussed how you determine whether a function increases or decreases by running a test on the derivative, and we check to see where it's positive, which would imply increasing, and where it's negative, which implies decreasing. We've talked about the first derivative test, which says that if there's a change from positive to negative, that you've hit a relative maximum. If there's a change from negative to positive in the derivative, you've hit a relative minimum. And now we're going to discuss concavity. And a function is said to be concave up. Loosely, we'd say it's concave up if it holds water. It looks like a bowl, basically. With calculus, we would say that the entire function of f lies above its tangent lines. So that if I were to go draw the tangent lines up here to a concave up function, you'll notice that it lies above them. Furthermore, the derivative, if you were to look at the derivative of these blue lines, the slopes of them, you would notice that they're very negative, and then less negative, less negative, less negative, less negative, and 0, then slightly positive, more positive, more positive, more positive, more positive. So you notice that the derivative is actually increasing. So let's take a look at, just a graph of the derivative loosely here. I probably won't put this in your notes, but when a function's concave up, what its derivative looks like is it's negative for a while, so it'd be below the x-axis, then it's 0, that would correspond to right here, and then it's positive. So it's an increasing function for the first derivative, which means the second derivative is going to be positive. Because when you're increasing, the derivative is positive. You would notice, for example, that the slope of this line is, say, maybe positive 2. So when the second derivative is positive, you'll notice we have a concave up portion of the graph. Concave down, similarly, looks like this, and we sometimes say that it sheds water. And the graph of f of x for a concave down function lives entirely below its tangent line. So I'm drawing the tangent lines right here in red. So f of x lies below its tangent lines. Likewise, the derivative right here, it's very positive, less positive, less positive, less positive, less positive, less positive, 0, slightly negative, more negative, more negative, more negative, more negative. So you'll notice that the derivative is actually decreasing. If I were to graph it, it would look like this. If I were to graph the derivative in a concave up portion of the graph, what's going to happen is it's going to start very much above the x-axis. It's going to hit 0, and then over here it's going to go more and more and more negative. So you'll notice that it is decreasing, hence the second derivative, the slope of the derivative graph, it's downhill, or it is negative. It's slightly important, but not super important, to note that f must actually be what we call twice differentiable. You must be able to take the second derivative in order for you to be able to determine concavity. So we have 4 situations with the graph. We have what we call concave up, which means it holds water, but it's also going uphill, which would be looking like this. This is concave up. The derivatives are increasing. Second derivative is positive. So we would call this concave up. This would have a second derivative that's positive. It's also increasing, so it would have a first derivative that's positive. Likewise, we have what we call concave up and decreasing. So what that looks like is the left-hand side of the bowl. It's still concave up, but it's a decreasing function. If you were to slide on it, you'd be going downhill. So its second derivative is positive because it's concave up. However, it's a decreasing function, so its first derivative is negative. Similarly, down here, with the concave down graphs, we can split them into 2 pieces. Concave down and increasing, which would look like you're going uphill, but you're concave down. So this would have a second derivative that's negative. Again, it's positive and less positive and less positive, so it's a decreasing function, which means its second derivative is negative. All right? And the f prime is be positive because I'm going uphill. Concave down and decreasing is like sliding down this hill. I am concave down, it is shedding water. The second derivative would be negative, and it's a decreasing function, so the first derivative would also be negative. So those are kind of the different portions that you have that involve both the second derivative. Whenever it's concave up, the second derivative is positive. to analyze the first derivative, we look at whether it's going uphill or whether it's going downhill. So on the next page, we've got what we call a concavity test, and I would like Ms. Shiro to pause this so you have time to write it. So if you take a pause, the graph of a twice differential function is concave up whenever the second derivative, if you can't read that, that's a second derivative is greater than 0, and concave down wherever the second derivative is less than 0. So basically a positive second derivative and a negative second derivative determine concavity. And an easy way to remember that is just with these smiley faces. If you have the second derivative, so we think of like 2 pluses, if you want to think of it that, being positive, then we open up, or we're concave up. If the second derivative is negative, then it's concave down and makes the negative face like that. What we run when we do the concavity test is I run a sign test again, but instead of on the first derivative, which is what we did when we were determining increasing and decreasing functions, or maxes and mins, we would run it on the second derivative. So let's say we take the second derivative and we determine it 0 at maybe 1 and 0 at maybe 4. Then what I do is I run a test on the second derivative in these intervals. If the second derivative is positive, and then say negative, and then maybe negative again, what this tells me is I'm concave up in this piece, concave down, and then concave down. You might say, well, how can it not alternate? Well, an example of a function that might result in that is one that is, say, concave up, so it's holding water, which means it's either looking like this or like this. I'll just go like that. And then what happens is the derivative is 0, and then it goes concave down, and then it's 0 again, and goes concave down. So you'll notice I've got what we would call right there a problem, but it didn't switch concavity. A concavity switch occurs when you go from concave up to concave down, but then when it continues to be concave down, there's no change. Most functions do alternate in their concavity, but not all of them. So let's go take just a generic example of a cubic function, and we are going to determine the intervals on which it's concave up or concave down. In concavity, the test requires me to take the second derivative. So I take the first derivative using my power rule, and obviously this is twice differentiable. It's a polynomial function, and they all are. And I would have my second derivative be negative 6x plus 6. So what I'm going to do now is determine where my second derivative is equal to 0, which would occur when 6x is equal to 6 or when x is equal to 1. So now I'm going to run my concavity test. I'm going to check in the second derivative. I've got 1 giving me a second derivative of 0. And what I'm going to do is test. And again, I'm testing now in the second derivative. Concavity is determined by the second derivative. Relative mins and max are determined by the first derivative. Increasing and decreasing are determined by the first derivative. But the concavity test says, go test these intervals. If you get a negative second derivative, it means we're concave down. If we get a positive second derivative, it means we're concave up. So we are going to go run a test. And the most logical thing to test in the negative infinity to 1 region would be the number 0. And again, I'm testing it in the second derivative. And when I put a 0 in for x, I get a positive. When I put maybe a 2 in for x in my second derivative, I get a negative. So I am concave up on the interval negative infinity to 1, non-inclusively, because at 1, I switch concavity, and that's coming up in the next set of notes. We actually have something that's actually called something where it changes in concavity, but we'll wait on that until the next set of notes. It's concave down on 1 to infinity. Now, if you were to take out your graphing calculator and graph this function, what it's going to look like is this. I'm not going to do the exact graph because I don't have my graphing calculator out, but what's going to happen is it goes like this, then like this, and then like that when you go graph the original f of x. And you'll notice right here at 1, comma 0, if you put a 1 in here, 0 would come out. I've got a change in concavity. I was concave, concave up or holding water right to about here, and then I had a switch and I started to shed water or be concave down right there. So I would have an interval of -1 to 1 for my downward concavity, upward I mean, and 1 to infinity for my concave down. All right, so the next one's going to get a little messy. We'll get as far as we can, and it's actually the derivative part of this one, but I'm going to run the concavity test once again. And when I'm done with this one, I think I'll be done. If I get cut off, then just go ahead and start the homework for 3.4. I'm not going to give any more notes. This will be it. So I am trying to determine intervals for concavity, which requires a second derivative. So the first thing I'm going to do is write this with a exponent so I can use my power rule. So I'm going to take the first derivative. I'm going to bring that power out front. I'm going to knock it down 1, but don't forget this is a composition, so I also have to do the derivative of the guts, which in this case is 2x. I'm going to clean that up and call it -12x times x squared plus 3 to the -2. All right? And then I am going to use, I could actually go ahead and, I could do product rule again, or I think I'll just, for practice, let's try writing this like that, and maybe we'll do a little review of our quotient rule. So right now I have to do the second derivative. Well, we have to do our low, d high, minus high, d low. Now be careful with d low. Okay, your derivative of your bottom function would be 2 x squared plus 3 to the first, but then times the derivative of the guts. So I would have that all written out. Then I would draw a line, and I'd square below, which would give me x squared plus 3 to the 4th. I need to clean up that numerator because I'm going to want to know where it's equal to 0. So with most polynomial functions, you've got to expand it all out, clean it up, and see what happens from there. So as far as I can get is as far as I'll take it in the time given. I've got x squared plus 3 squared, which would be x to the 4th, plus 6x squared plus 9 when I FOIL it. I need to multiply all of that by a -12. I'll put it out front, and I'll do that in a minute. 2 negatives make a positive, so I'll take care of that. I've got 12 times 2 times 2, which is going to give me, what's that going to give me? 48, I believe. Yes, 48. And I also have the 2 x's in there, so I'll have x squared, and then it's times x squared plus 3. And I'm only worrying about the numerator right now, so I know this is on the bottom, but let me continue with the cleanup of the numerator. So, distributing the -12 in, I have -12x to the 4th minus 72x squared minus 108, yuck. Then it's plus 48x to the 4th, and then plus 144x squared. Now cleaning that up, these will combine, giving me 36x to the 4th. These will combine, giving me 72x squared, and I have a minus 108. That is the top of my fraction, and it's all over x squared plus 3 to the 4th power. All right, so basically, I did my product rule to get the first derivative. I did the quotient rule to get my second derivative, which was a beast. And now I want to know where is it equal to 0. And for a function to be equal to 0 when it's rational like this, it means the top has to be 0. So I get to ignore the bottom. So I want to know where's the top equal to 0. And you should notice that a 36 factors out of there. So I'm going to factor a 36 out of the top, and I'm ignoring the bottom. It doesn't matter what that is right now. And factoring it further, I would have x plus 3 times x. Oh, and that was x to the 4th. Sorry, so this should be a 4th and a squared. Sorry. And then I'd have x squared minus 1. Did I get that cleaned up? Sorry, I forgot about my 4th degree polynomial there. So basically, what I'm left with here is the only way 36 times these two can be 0 is if x squared minus 1 is 0. This is always positive, it's always positive, which means x is equal to plus or minus 1. Those are the points I'd have to test for Concavity. I do -1, 1, and I test them in the second derivative. And what happens with that one is it ends up